we'll start it in 2 minutes. Okay, all right, we'll start now. Good afternoon, everyone, and I am Kartika. I am the TA for the problem solving sessions for the NPTEL course Fluid and Particle Mechanics. The course code is NOC25CH49 and course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. So since this Fluid and Particle Mechanics is a 12 weeks course, and we have seen the course layout as well in the previous lectures. The idea behind the problem solving session is that to help you in clearing doubts related to problems or assignments of that week, and we will solve problems also, so that it will be helpful in your assignment submission. That is one thing, and you can recollect these problems for your final exam as well. And your final exam comprises some percentage of marks from your assignments as well. So submit your assignments on time. That is one thing. And if you have any doubts, you can ask me. So the course lectures, those videos given by the professors are already in the NPTEL website. These are just to have a interactive session with that week's problems. So not anything new. We won't be seeing concepts. Mostly we will be seeing the problems. And if you have any doubts in those sessions, we can clear that as well. So now let us see. So as I mentioned, it is a course of 12 weeks course, and we have seen introduction to Navier-Stokes equation and their exact solutions, Poiseuille flow, and second week it is Taylor-Couette flow and rheology. Third week it is dimensional analysis. Fourth week it is turbulent flow. Fifth week friction losses Moody's chart. Sixth it is boundary layer theory. Seventh introduction to particles, their characterization, and eighth it is particulate phenomena. And ninth, motion of particles in a fluid, terminal velocity, particle separation, sedimentation of dilute, concentrated and flocculated dispersions, packed and fluidized beds, and filtration. So it is mostly covering half of the courses about fluid mechanics and half is about particle mechanics. So maybe even though we will be covering all the syllable content mentioned over here, there might be some we might not be sticking exactly with the layout. So now for books and references, we have unit operations of chemical engineering by McCabe and Smith, And second, fluid mechanics, Frank M. White. And third, introduction to particle technology. And few references. First one is Coulson and Richardson's chemical engineering. And second, it is fluid mechanics by Piyush K. Kundu. And third, it is principles of colloid and surface chemistry. And last one is transport phenomena by Bert Stewart and Lightfoot. Bert Stewart Lightfoot. So this is these are for the books and references. Now coming to week 6, what we are going to see is sedimentation and separation, settling velocity, Stokes regime and Newton's regime, applications of settling 2, and colloidal aggregates, settling of colloidal aggregates. So now let us start with problems. In the beginning itself, let me tell you, in this week, it is about application of a single formula for different things. That is what we are going to see. Mostly it is about terminal settling velocity and a few concepts based questions here and there. So we have almost 16 problems for today's session. So now let us move on to the session. If you are having any doubts during the session, you can ask me that time, or you can stop me and ask later as well, whichever is convenient you can do. I'll just keep volume, check everything. All right, okay, we'll start now. So for question 1, what we have got here is match the following. The notations used here are D for diameter, R for radius, subscript P for particle, rho for density, mu for viscosity, etc., as those used throughout the course. So it is a simple match the following problem, and the notations are which we regularly use. That is D for diameter, R for radius of the particle, and rho for density, mu for viscosity, P for subscript P for particle. So now we have to match the ones on this side with those on the other side. So we have a few options. Let us first look at the options. First one, option A, X, B, 1, okay, A 10, B 1, C 7, D 2, E 8. And option B, it is A 2, B 1, C 2, D 4, E 10. And option C, it is A 1, B 2, C 3, D 4, E 5. And option D, it is A 5, B 10, C 7, D 2, E 11. So now I'll give you a 1 minute time. So we have to match everything in the left hand side of the column with the right hand side. So what have we got in the left hand side? We got Stokes settling velocity, Newton's settling velocity, Stokes-Einstein relation, and Einstein's theory of diffusivity, and Brownian force. So just look at it and match it with the relevant thing. I'll give you a 1 minute time. So after that, we will discuss what each of these mean and what exactly is the right answer that we are matching with the other things. So yeah, now we'll discuss the answer right now. So answer is, can anyone say what the answer is? So if we don't know the later three also, but we know the simple formula for Stokes and Newton settling regime. So based on that, we can actually identify the right one. So first one, it is Stokes settling velocity, which we have been repeatedly using. So it is 10 dp square into rho p minus rho into g by 18 mu. And second one we have Newton's settling velocity, and it is starting with 1.75 into square root of dp into rho p minus rho into g by rho. So that is for Newton's settling velocity. So this is Stokes settling velocity, this is Newton's settling velocity. So Newton's settling velocity, similar things are in 1 and 5. How can we differentiate which is the right answer? If in case we forget what is the option, we can do dimension matching and find it out. So for example, it is dp is meter, rho p minus rho is kg by meter cube into meter by second square divided by kg by meter cube. So this and this gets cancelled in terms of units, and we will be left with meter into meter by second square. So it becomes meter square by second square to the power of 1 by 2. So it is a square root, so it becomes meter per second. So that is a settling velocity relation. Whereas in the fifth, if we see, it is meter into kg by meter cube into meter per second square divided by kg meter per second, kg per meter second, kg per meter second. So kg gets cancelled, and meter per meter second goes there. Meter into meter second by into meter by second square. So it becomes meter cube by second, something along that line, to the power of 1 by 2. So again, that won't be the formula. So you can right away go with 1. So A is 10, B is 1. So that option we can correctly match it with option A. So A 10, B 1, and next we have Stokes-Einstein relation. So that is C7. So 7 we have D is equal to KBT by 6 pi mu RP. And D we have Einstein's theory of diffusivity, which is actually D2. So here it is, limit of t approaching infinity, delta r square into t, r square of t is equal to 6 dt. And finally we have Brownian force, which is given by 8, so it is kbt by rp. So option A is the right answer. A 10, B 1, C 8, C7, D 2, E 8. So now we will look at explanation for one by one. So first one is Stokes settling velocity. Stokes' law describes the settling velocity or terminal velocity of a small spherical particle in a viscous Newtonian fluid under the influence of gravity, assuming a lower Reynolds number. So whenever we are talking about Stokes regime, it just means that Reynolds number is very low. When Reynolds number will be very low, Reynolds number is given by rho v dp by mu. So if we are having a very high viscous effects, we can call it to be under the influence of Stokes regime. So if there is a high viscous dominant force acting on the system, Reynolds number will be low. Whereas if viscosity is low, Reynolds number will be very high comparatively. So Stokes regime won't be valid in that case, whereas Stokes regime will be valid in the low Reynolds number case, or in other words, we should have a highly dominant viscous viscous effects to be felt under that particular thing. So RET is equal to rho v dp by mu. So in Stokes regime, as we have seen, it should be lower value. So we can say that of a small spherical in a viscous Newtonian fluid under the influence of gravity, assuming a low Reynolds number or a creeping flow. Settling velocity Vs is given by Vs is equal to rho p minus rho f g into dp square by 18 mu. Here S is just a notation used by myself here. You can vary it, Vt anything, okay. And where g is the acceleration due to gravity, dp is the particle diameter, and rho p is the density of particle, rho f is the density of fluid, and mu is the fluid viscosity. So these are all the terms given over here. This equation shows that the settling velocity depends on the difference in density between the particle and the fluid, acceleration due to gravity, particle diameter, and fluid's viscosity. So just what are all the things that influence the settling velocity? That is what we are seeing over here in this relation. So looking back, Stokes law describes the settling velocity or terminal velocity of a small spherical particle in a viscous Newtonian fluid under the influence of gravity and assuming a low Reynolds number. So Vs is equal to rho p minus rho f into g into dp square by 18 mu. So g is acceleration due to gravity, dp is the diameter of the particle, and rho here is the density, and rho p means density of particle, rho f means density of fluid, and mu is the fluid viscosity. So when we say it is Stokes regime, when it is having a high viscous effects or a low Reynolds number flow, so that time we call it as a Stokes regime. So the formula is given over here. You can also do force balance and get it, but easy way is remembering the formula, because we will be repeatedly using these formula and all for everywhere whenever we are talking about fluid particle mechanics. So better to remember it now only. Next is Newton's settling velocity. So Newton's settling velocity, Newton's law regime for particle describes the process when a particle in a fluid has a higher Reynolds number. So previously we had low Reynolds number and now we have high Reynolds number. Typically, high Reynolds number typically 1000 to 2 lakhs, resulting in a constant drag coefficient. Settling velocity and terminal settling velocity can be calculated using the equation. So what happens is that we have generally this is the plot which we use in most of the cases whenever we are talking about settling of a single particle or even multi-particle depending on system we are using. But in general, I am talking about a CD versus REP relation for a single particle settling in a fluid. So this is the low Reynolds number region and this is the high Reynolds number region. For sphere, it would be like a 0.4, this particular value. Like it would be like a constant thing and the value would be 0.4. Whereas this is the Stokes regime, this is the Newton's regime, high Reynolds number, and that is the low Reynolds number. In Stokes regime, what happens? We are able to see a drop in drag coefficient with increase in Reynolds number, whereas at higher Reynolds number, we are able to see the drag coefficient remains the constant. So that's why we are saying that Newton's law regime for a particle settling under the process when a particle in a fluid has a higher Reynolds number, resulting in a constant drag coefficient of 0.44 and a terminal settling velocity that can be calculated using the equation Vt is equal to 1.75 into square root of g into dp into rho p minus rho f by rho f. So here again, this is what we have seen in the question as well. So g is meter per second square and dp is meter, rho p minus rho f and rho f gets their units cancelled. So ultimately we will receive a terminal settling velocity as meter per second. So what is the formula? Newton's law regime describes the process when a particle in a fluid has a higher Reynolds number. When the particle will have higher Reynolds number? When it is settling in a low viscosity fluid, or its diameter can be large or density can be large, whatever. So if that is the case and we are getting a very high Reynolds number, typically in the range of 1000 to 2 lakhs, we have the constant drag coefficient which I described in the figure. So that drag coefficient is around 0.4, that is 0.44, and its terminal settling velocity can be calculated using this formula where Vt is equal to 1.75 into g into dp into rho p minus rho f by rho f into square root. So here Vt is the terminal velocity, g is the acceleration due to gravity, rho p minus rho f is again a density difference between the particle and the fluid, and rho f is the fluid density. So third one we saw Stokes-Einstein relation. In Stokes-Einstein relation, what we are going to see, the Stokes-Einstein equation, also known as Einstein-Stokes equation, relates the diffusion coefficient of a particle to the viscosity of the surrounding fluid and the particle size. It essentially describes how quickly a particle diffuses through a liquid due to random motion and how that diffusion is affected by the fluid's resistance to flow. The equation is typically described as d is equal to 6 d is equal to kBt by 6 pi mu rp, and here d is the diffusion coefficient and kb is the Boltzmann constant and T is the absolute temperature, mu is the dynamic viscosity and rp is the hydrodynamic radius of the diffusing particle. So what does Stokes-Einstein relation or Einstein-Stokes equation say? It relates the diffusion coefficient to the particle's viscosity, to the viscosity of the surrounding fluid and the particle size. So here if we say d is equal to d is equal to kBt by 6 pi mu rp, so we can say that diffusion coefficient is a function of dynamic viscosity of the fluid and the uh, hydrodynamic radius of the diffusing particle. So d is equal to 6 kBt by 6 pi mu rp. So d is the diffusion coefficient and kb here is the Boltzmann constant. T is the absolute temperature, mu is the dynamic viscosity of the fluid and rp is the hydrodynamic radius of the diffusing particle. So we are saying that how a diffusion is happening and what are all its functions. So it is diffusion is coefficient is inversely related with the particle size and the fluid viscosity. So it relates coefficient of diffusion coefficient of a particle to the viscosity and the particle size. So it basically what it is trying to describe is how particle can quickly diffuse through a liquid at a random motion and how that is affected by the viscosity of the fluid. So viscosity is the resistance of the fluid to move, right? So that is what it is saying. And fourth one we have Einstein's theory of diffusivity. So Einstein's theory of diffusivity describes how particles move randomly through a medium due to the thermal motion, resulting in net movement from areas of high to low concentrations. So it just describes how a particle moves randomly through a medium due to the thermal motion. So when there is a heat, it results in the motion of particles and how it moves and its net movement from areas of a higher concentration to our areas of lower concentration. Like we all would have studied, right? To maintain the equilibrium, it moves from a higher to lower end. So he formulated the Einstein-Smolowski equation relating the diffusion constant d to the mean squared displacement of a particle del square over time, and displacement is delta and diffusion constant is d and time is t. So d is equal to delta square by 2t. So when we take limit, it is limit of t approaching infinity. So del r square or t is equal to 6 into d into t. So in here d is the diffusion constant. This foundation work also established the Einstein relation between particles mobility and its diffusion coefficient, allowing for the calculation diffusion from other properties. This is a fundamental result from Einstein's theory of Brownian motion, stating that the time averaged mean square to displacement delta r square of t of a particle undergoing diffusion grows linearly with time. That is 6 into d into t over long times, where d is the diffusion coefficient and t is time. This equation quantifies random continuous movement of particles and shows that while individual displacements are unpredictable, the average displacement grows predictable over time. So that is what is question Einstein's theory of diffusivity. I am not going very in depth into it because people might be already aware. So without like we'll move to the last, that is the Brownian force. This is the core formula describing the Brownian motion. The diffusion coefficient itself is often calculated using Stokes-Einstein relation, that is given by d is equal to kBt by 6 pi eta r or mu r, and kb is the Boltzmann constant, so we can say d is equal to kBt by rp. and T is the absolute temperature, Kb is the Boltzmann constant, and Rp is the radius of the particle. So these are for question 1. So what we did is, we have just seen how all things are, what are all things are. So on the left hand side we have Stokes settling velocity and Newton settling velocity, and Stokes Einstein equation, Einstein's theory of diffusivity, and Brownian force. So for this first Stokes settling velocity, we know that it is at the low Reynolds number regime, and we take viscous effects to be very high in those regions. Next is the Newton settling velocity. So it is having a Reynolds number range of 1000 to 2 lakhs, and at, as I mentioned, at a higher Reynolds number we will be having drag coefficient as constant of 0.44, and terminal settling velocity can be calculated using the formula given over here. So these two formula are very familiar with us, which we with us in the sense, as I mentioned, as chemical engineers. So next one is Stokes-Einstein relation, wherein we have seen about how diffusion constant is varying as a function of particle radius and viscous resistance to flow. And Einstein's theory of diffusivity, how a particle is moving randomly through a medium due to its thermal motion, and resulting in motion from higher to lower concentrations. And finally we have Brownian force. So it is like D is equal to kBt by 6 pi mu r p mu rp, and D is equal to kBt by rp. So kBt is the Boltzmann constant, rp is the radius of particle, T is the absolute temperature. So this is for question 1. I hope it is clear. Now we have question 2. In question 2, what is asked? The total drag force acting on a particle is a function of dash. The total drag force acting on a particle is a function of dash. Option A, particle drag coefficient. Option B, projected area of the particle. Option C, both 1 and 2. Option D, none of the above. So again, I'll give you guys a minute time, so we will discuss the answer. If you get the answer, let me know. So answer is actually option C, both 1 and 2. Drag force acting on a particle is a function of drag coefficient as well as the projected area of the particle. So that is the answer. Answer is therefore option C. Now we will see how option C is the right answer. Okay, we haven't given here, but drag force acting on a particle, we know the formula, right? Total drag force. So it is a function of particle drag coefficient as well as the projected area of the particle. So basically, total drag force acting on a particle is a function of drag coefficient, projected area of the particle, density of fluid, and square of particle velocity. It can be expressed as Fd is equal to half CD rho A into V square. F is equal to CD rho A V square. So it is a function of projected area, that is this A, and it is a function of drag coefficient. So it is a function of both. Option C is the right answer. Now we will go to question 3. The particle Reynolds number is a function of dash. So I think you all know the answer to this, right? So we will just recollect Reynolds number. It is Reynolds number is equal to rho into V into dP by mu. So rho here is the relative density between the fluid, and rho is the density of fluid, not relative density. Rho is the density of fluid. V is the relative velocity between fluid and the particle, and dP is the diameter of the particle divided by mu. Again, mu is the viscosity of the fluid. So particle Reynolds number is a function of particle density, option B surface tension, option C particle diameter, option D both A and B. Okay. So as I mentioned, Reynolds number is given by RET is equal to rho into VT into dP by mu. So rho is the density of fluid, not particle, and Vt is the relative density, and dP is the diameter of the particle divided by mu. Mu again is the viscosity of the fluid. So answer is, it is not a function of particle diameter. It is not a function of surface tension, and the answer is option C. It is a function of particle diameter. It is rho V dP by mu. So answer is option C is the right answer. Oh, we have one more option, that is option E, that is none of the above. But we know that answer to this particular problem is option C, that is particle diameter. Oh, yeah. Option C is the right answer. Now we will move on to question 4. REP particle diameter is a function of rho V dP by mu. Particle Reynolds number is not a function of dash. Option A acceleration due to gravity. Option B pipe diameter. Option C surface tension. Option D all of the above. Option E none of the above. So what do you people think is the right answer? Because we have just discussed it right now. No? So particle Reynolds number is not a function of dash. Option A acceleration due to gravity. Option B pipe diameter. Option C surface tension. Option D all of the above. Option E none of the above. So answer is REP is equal to rho into V into dP by mu, and here none of it is applicable. We don't have G in REP formula, we don't have pipe diameter. It is not pipe diameter. Whenever we are talking about particle Reynolds number, it is particle diameter. So option B is also false. Finally, we have option C surface tension. Surface tension is also false. So it is all of the above is the right answer, option D. So whenever we are talking about Reynolds number, we have a different Reynolds number like flow Reynolds number, particle Reynolds number. We need to make sure in what context we are talking about, because mostly it is rho v d by mu or rho v l by mu, where L is the characteristic length which varies depending on what we are talking about. In some cases, it would be the length of the channel, or it would be the diameter of the pipe, or we can even use hydraulic diameter, or in case of particle it is particle diameter, whichever it is. So we should be aware of what we should use there. In general, in general, Reynolds number is equal to rho into v into characteristic length by mu. So that is the formula. So now we got the right answer, that is none of these belong in the Reynolds number formula. So option D, all of the above is the right answer. Again, REB is equal to rho v dp by mu, because here we are talking about particle Reynolds number, so we are using dp, that is characteristic length, as dp, diameter of the particle. So that is for this question. If you have any doubts, please stop me. Okay. So next is question 5, where we got uh, spherical particles of density 2500 kg per meter cube and in the size range of 20 to 100 micrometer are fed continuously into a stream of water whose density is 1000 kg by meter cube and viscosity is 0.001 pascal second, flowing upward in a vertical pipe. Diameter of pipe is 100 times the diameter of the largest particle. What is the maximum water velocity required to ensure that no particles larger than 50 micrometer are carried upwards with the water? Report your answer in per second. So what is asked, we are given that we have a spherical particle whose density is 2500 kg by meter cube, and its size range is given as 20 to 100 micrometer, and we are feeding the particles continuously into a stream of water, and its density is 1000 kg per meter cube and viscosity is 0.001 pascal second, and it is flowing upwards in a vertical pipe. So diameter of pipe is 100 times the diameter of the largest particle. So wall effects won't be coming into picture here. What maximum water velocity is required to ensure that no particles larger than 50 micrometer are carried upwards with water? Report your answer in per second. So we should ensure that larger particles larger than 50 microns are not carried upward with the water. So their terminal velocity should be controlled. So now we will see how to do that. So question 5 solution. So first let us write given. Given is particle diameter is 50 micron. So 50 micron, above 50 micron it should not go. And particle density is 2500 kg per meter cube. And fluid density rho f, fluid is water here, so its density is 1000 kg per meter cube, and its viscosity is 0.001 pascal second, and pipe diameter is given as 100 times the particle diameter. So pipe is large compared to particles, so there is no wall effects. So these are all the things which are given. To find velocity, water velocity. Okay. Maximum water velocity. Formula is again like a terminal settling velocity formula only. Vt is equal to rho p minus rho f into g into dp square by 18 mu. So now we have to substitute everything. Vt is equal to rho p minus rho f. Rho p here is 2500 minus 1000 into g 9.81 into dp square 50 into 10 power minus 650 microns. So 50 into 10 power minus 6 meters to the square divided by 18 mu, that is 18 into 0.001 or 0.18 into 1 into 10 power minus 3. So VT we will get as 2.0438 into 10 power minus 3 meters. Since in the question it was asked that 2.04 mm, asked to report in mm per second, the answer is 2.04 mm per second. So in the question what was asked is we have to identify what value of the water velocity should be maximum water velocity to ensure that particles greater than 50 microns are not carried in the water. So we have used this. So what do you think is the relation between terminal settling velocity and the question given over here? Can anyone tell? Okay, so whenever we are talking about terminal settling velocity, what do we mean by or in other words, what can I ask? Terminal settling velocity. So terminal settling velocity, I mean, what do we mean by terminal settling velocity? Terminal settling velocity is the constant speed in which the particle is falling through a fluid when we balance the gravitational force and the buoyancy force and drag force. So there is zero acceleration. So that is called as constant terminal settling velocity. So when a particle is entering a fluid, it accelerates under gravity. So when with increase in the particle speed, the fluid's drag, which is opposing the motion, decreases. Eventually, what happens? The drag becomes equal in magnitude to the net gravitational force, net downward force, gravitational force minus the buoyancy force. So what happens when the forces are balanced? The net force on the particle is zero, and acceleration therefore stops. If acceleration stops, it is a constant velocity. So terminal settling velocity is a parameter in industry. I mean, it is very key parameter in various industries. Mainly in mineral processing industries, for separation and all, terminal settling velocity is very important. So in this particular question, what is being said is we have used the terminal settling velocity. So when water velocity is greater than this velocity, uh, we we can ensure that particles greater than 50 microns won't be like escaping in the water stream, because this is the terminal settling velocity. So if water velocity if water velocity, if this is the maximum water velocity, we can ensure that the particles greater than 50 microns won't escape into the water stream, because what to say, for particles greater than 50 microns, their terminal velocity will be higher than this. So in that case, they can't escape into the water stream. So in the question, it was clearly asked that spherical particles of density 2500 kg per meter cube and in the size range of 20 to 100 micrometer are fed continuously into a stream of water whose density is 1000 kg by meter cube and viscosity is 0.001 pascal second, flowing upward in a vertical pipe. The diameter of the pipe is 100 times the diameter of the largest particle. What maximum water velocity is required to ensure that no particle larger than 50 microns are carried upwards with the water? So this is the maximum water velocity which we require, so that we can say that no particles larger than 50 micrometer can be carried upward with the water, because their terminal velocity will be higher than that. So that is the case. Mm. So we just found out the terminal settling velocity. So it is a very simple straightforward problem. Now we will go to question 6. In question 6, estimate the largest diameter of the spherical particle of density 2000 kg per meter cube, which would be expected to obey Stokes settling velocity in air. Once again. Okay. Estimate the largest diameter of spherical particle of density 2000 kg per meter cube, which should be expected to obey Stokes settling law in air of density 1.2 kg per meter cube and viscosity 18 into 10 power minus 6 pascal second. Report your answer in micrometer. So what is asked? What is the largest diameter of the spherical particle whose density is 2000 kg per meter cube and that is expected to obey the Stokes settling law in air of density 1.2 kg per meter cube and viscosity 18 into 10 power minus 6 pascal second. So we are asked to find the diameter of the sphere which still obeys the Stokes settling law, or it is still in the Stokes regime. And the sphere diameter is 2000 kg per meter cube and air density and viscosity are given as 1.2 kg per meter cube and 18 into 10 power minus 6 pascal second. So generally what happens is that we Stokes regime we use Vt is equal to rho p minus rho f into g into dp square by 18 mu. So that is the formula. In that formula, what do we know? Rho p minus rho f we know because particle density is given as 2000 kg per meter cube and rho f is given as 1.2 kg per meter cube. Rho p minus rho f into g is 9.81 into dp square. Dp square diameter of particle is unknown divided by 18 mu. Mu is given as 18 into 10 power minus 6. So and Vt is unknown, dp is also unknown. So what can we do? We are asked to ensure that Stokes regime must be maintained. So for Stokes regime, the maximum Reynolds number can go is up to 1. So we can use rho v dp by mu is equal to 1 and dp we can keep it unknown and Vt we can calculate it as a function of dp. So Vt dp is equal to 1 into mu by rho and we can substitute all the nodes and we can take Vt as a function of dp and substitute Vt in the Stokes law and we can get dp value, that is the maximum or the largest diameter of the sphere. So that is how we need to do. So since I gave the steps, I'll give you guys 1 minute time. Just take that time and analyze the answer. I will try finding out the answer. I just gave the steps. So what we need to do, we need to take the Stokes law and in that Vt will be unknown, dp will be unknown. So to find Vt, we'll take Reynolds number equation and put it as 1 and get Vt as a function of dp and again put it in the first equation and we have to finally calculate the dp. So that is the steps. Just take a minute to give the answer. Okay, we'll just see the steps now. Solution, that is, given particle density 2000 kg per meter cube, fluid density 1.2 kg per meter cube, fluid viscosity 18 into 10 power minus 6 pascal second, and valid for Reynolds number less than or equal to 1. That is the Stokes regime. So solution, set RET is equal to 1, maximum for Stokes law validity, and RET is equal to rho Vt dP by mu. So mu is known, rho is known, Vt dP are unknown. Substitute Vt from the Stokes equation. So okay, Vt is equal to rho p minus rho f g into dP square by 18 mu. So yeah, we can use this and substitute back, or we can, like both the way it works. Both will lead to same solution, and it was rho Vt dP by mu. So rho is there, and Vt we put rho p minus rho f g into dP square by 18 mu dP by mu equal to 1. So what happens now? Rho f remains rho p minus rho f g into dP cube, dP square, and dP becomes dP cube by 18 mu square equal to 1. Now substituting everything, so rho f is 1.2, rho p is 2000, rho f is 1.2 kg per meter cube again, g is 9.81, dP is unknown, divided by 18 mu square. So mu is 18 into 10 power minus 6 pascal second. So we have substituted that, equal to 1. So now on calculating this, we will be able to find out dP value in micrometer. So we'll just do the calculation. I'll just do the calculation once again, just for confirmation, nothing else. 18 into 10 power minus 6 into 18 divided by 1.2 divided by 9.81 divided by 2000 minus 1.2. So we will be getting dP cube is equal to 2.4786 into 10 power minus 13. So now we need to take the cube root of that, and we will get it as 6.2815 into 10 power minus 5 meter, or we can write it as 62.815 into 10 power minus 6 meter, or that is 62.815 micrometer. So that is how we calculate. So it is a very simple problem. So what we did, we are asked to find the largest diameter of the sphere which can maintain the Stokes regime, which should be expected to obey Stokes settling law in air. Air is a very difficult, right? So it is in air of density 1.2 kg by meter cube and a viscosity 18 into 10 power minus 6 pascal second. So why, like in air it is very difficult? Because air viscosity is very low, so it is very difficult to have a viscous effects. So without viscous effects, we can't, have the Stokes regime. It would be Newton's regime so easily. So again, to maintain that, Re is equal to, Reynolds number is equal to rho v dP by mu. So if mu is very low, Reynolds number increases. So again here density is also low. So density is low, mu is very low. So it is like somewhat low value. So what we can adjust is, we can adjust the diameter of the particle. So in that basis it was asked. So the particle density rho p is equal to 2000 kg per meter cube, and density of fluid and viscosity of fluid are given. So Reynolds number is condition is less than or equal to 1. So we put equal to 1, and rho v dP by mu equal to 1, and again for v we are getting it from the Stokes regime. Stokes regime states that V is equal to G dP square, rho P minus rho F into G into dP square by 18 mu. So we are substituting it in the Reynolds number equation and we are getting one equation which will give us dP cube, and dP we will get it from there. So that is the how we do the solution. So now finally it is question 7. Yeah. In question 7, what is asked? Consider a spherical particle of diameter dp and radius rp of mass mp moving through a fluid in one dimension under the action of gravity, and g is the acceleration due to gravity with a constant velocity u. Assume the density of fluid to be rho and that of particle to be rho p. The viscosity of the fluid is mu. So we are given the nomenclatures for a particle settling in a fluid, and fluid parameters like diameter, density, mass, etc. has dp, rho p, mp, and fluid parameters like density and viscosity has rho and mu without any subscripts. So force of gravity acting on the particle is dash. So whenever we are talking about fluid and a particle settling on fluid, we talk about like it is being pulled by the gravitational force, and we have buoyancy force, we have drag force, everything. So in this question it is asked what is the force of gravity acting on the particle. So Fg is equal to basically force gravitational force of gravity is equal to, here we are not asked in terms of anything, so we will go with the straightforward approach. So Fg is equal to mpg. So it is the mass of the particle pulled down by the acceleration due to gravity. So that multiplying those two gives us the gravitational force. And if we need to write it in terms of diameter of the particle, what we can do, uh, mass of the particle is equal to density into volume. So density into volume gives us mass. So rho p into vp gives us mp. So rho p is here fixed and vp is, since it is a spherical particle, its volume is pi by 6 dp cube. So we know mp is equal to rho p into pi by 6 dp cube. So substituting this in here gives us Fg is equal to rho p into pi by 6 dp cube into g, because we are asked to find the force of gravity acting on the particle. We can straight away give it as mpg, or more detailed manner it would be rho p into pi by 6 into dp cube by dp cube into g. So that is the thing for question 7. Now let us go to question 8. The buoyancy force acting on the particle is dash. So before moving on to this particular problem, we'll take a short 5 minutes break. No, like time now is 4 o'clock. We will resume, okay, 4:1, we'll resume by 4:5. Okay, all right. Thank you. Alright, we'll start now. Oh, I kept the solution, I guess. Oh. B. Okay, we'll start now. The buoyancy force acting on the particle is dash. So now we need to calculate the buoyancy force. So the buoyancy force acting on a submerged object is given by Archimedes principle. So buoyancy force is equal to the weight of the fluid displaced by that particular object, and for a spherical particle of diameter dp submerged in a fluid of density rho, volume of displaced fluid is equal to volume of sphere is equal to pi by 6 dp cube. So okay, we can keep it as small d here because everywhere else we have used small dp. So what is buoyancy force? It is the force acting on any submerged particle, and it is object and it is given by Archimedes principle. The buoyancy force is equal to the weight of the fluid displaced by the object, and for a spherical particle of diameter dp and which is submerged in a fluid of density rho, and it is given by like if a particle is submerged in a liquid, the volume of the fluid displaced by the particle will be equal to the volume of that particular particle. So in that context, volume of displaced fluid is equal to volume of spherical particle equal to pi by 6 dp cube, and the weight of displaced fluid will be volume of displaced fluid into density of the fluid. So that weight of displaced fluid into gravity gives us the buoyancy force. So are you understanding my point? So it is volume of displaced fluid is pi by 6 dp cube into density of fluid is rho. This gives us the weight of displaced fluid, and into g gives us the acceleration due to gravity. If not, what we can do is we can write it here. Alright, are you understanding? So what we are doing, we are asked to find the buoyancy force acting on the particle. So buoyancy force acting on the particle is nothing but it is given by the Archimedes principle. So it is buoyancy force acting on the particle equal to mass of the fluid displaced by the particle into g. So mass of the fluid displaced by the particle will be given by volume of the fluid displaced by the particle into rho of the fluid, density of the fluid. So that is what we are going to find here. So buoyancy force is equal to the weight of the fluid displaced by the object m into g, And for a spherical particle of diameter dp submerged in a fluid of density rho, volume of displaced fluid is equal to volume of sphere, that is pi by 6 dp cube, and weight of displaced fluid is equal to volume of displaced fluid into density of fluid, which is given by rho pi by 6 dp cube into rho. Okay, this is not weight actually, here it is mass. Weight is this mass into g. So volume of weight of displaced fluid is given by buoyancy force. That buoyancy force is equal to volume of displaced fluid into density of fluid into g, and it is finally equal to pi by 6 dp cube into g. So I hope you understood this question. Now we will go to next question, question 9. The drag force acting on the particle is dash. Drag force acting on the particle is drag dash. Drag force acting on a spherical particle moving through a fluid depends on the flow regime, but for low Reynolds number, that is Stokes flow, it is given by Stokes drag law. Drag force, that is Stokes law, is given by Fd is equal to 6 pi mu Rp into U. So it depends on the flow regime, but for low Reynolds number flow or Stokes regime, it is given by drag force is equal to 6 pi mu Rp into U. So this is the drag force acting on a particle, and here Fd is the drag force and mu is the viscosity of the fluid. Rp, mu is the dynamic viscosity of the fluid. Rp is the radius of the particle. U is the velocity of the particle relative to the fluid. That's it now. Yeah. And it is the radius of the particle. Now we will go to question 10. Most of the questions in this week's assignments, as far as I have seen, is mostly theoretical questions. So I hope you would have, like submitted your assignments way back. But if not, please utilize this. Consider a spherical particle of diameter dp of mass mp moving through a fluid in one dimension under the action of centrifugal force. Assuming r to be radius of path of particle and omega to be the angular velocity in radians per second with a constant velocity u. Assume the density of the fluid to be rho and that of the particle to be rho p. The viscosity of the fluid is mu. The centrifugal force acting on the particle is dash. So solution is, since the particle is moving under centrifugal force instead of gravity, the actual gravitational force is Fg is equal to mpg. Is not a very dominant force here. Centrifugal force acting on that particle, that would be Fc is equal to m omega square r. So basically, so how to V is equal to r omega. So this is the centrifugal force acting on the particle, and that if we put m is mass of the particle, and here it is rho p into pi by 6 dp cube, because it is density into volume of the particle, that is volume of sphere. So m is equal to rho p pi by 6 dp cube into omega square into r. So that is the thing. I can remove this as well. Or I can remove this. All I guess. Now we will go to question 11. Now all the coming up questions are based on centrifugal force and not like a normal settling. The buoyancy, so if we want to read question once again, we will read it. Consider a spherical particle moving through a fluid in one dimension under the actions of a centrifugal force. The Assume r to be the radius of the path of the particle and omega to be the angular velocity in radians per second with a constant velocity u. Assuming the density of the fluid to be rho and that of particle to be rho p. Whereas in the previous question, if you remember, consider a spherical particle moving through a fluid in one dimension under the action of gravity. Whereas here it is under the action of centrifugal force. So that is the difference, but everything else is same. Centrifugal force acting on the particle is u because here it is under the action of centrifugal force. So it is mp into omega square r. So it is rho p pi by 6 dp cube omega square r, because mp is equal to density into density of particle into volume of particle, which is given by density of particle is rho p and volume of particle is pi by 6 dp cube. So that is for question 10. In question 11, what is asked? The buoyancy force acting on the particle is, the buoyancy force acting on a submerged object is again given by Archimedes principle. The buoyancy force is equal to the weight of the fluid displaced by the object. For a spherical particle of diameter dp submerged in a fluid of density rho, volume of displaced fluid is equal to volume of sphere is equal to pi by 6 dp cube. And here it is weight of displaced fluid. So we can write one more line. Mass of displaced fluid is equal to buoyancy force V is equal to pi by 6 dp cube, or it is pi by 6 dp cube into rho, and weight of displaced fluid is volume of displaced fluid into density of fluid into g, or pi by 6 dp cube rho g, or here it is not under the influence of gravity, it is under the influence of centrifugal force. So it is pi by 6 dp cube rho into r omega square. So that is the answer. So here what can we write? Here we can under the action of centrifugal force. Gravitational force. So that is for question 11. Now for question 12. Question 12 is actually a repetitive question. The drag force acting on the particle is dash. So drag force acting on a spherical particle moving through a fluid depends on the flow regime, but for low Reynolds number, Stokes fluid is given by Stokes drag law. Drag force is 6 pi mu rpu, and we don't have anything changed. Mu is the dynamic viscosity of the fluid, rp is the radius of the particle, and mu u is the velocity of the particle relative to the fluid. So again here it is radius. We got three problems more, and we have a lot of time left, so we can go slow also, not an issue. But anyway, this is the drag force acting on the particle. And now coming to question 13, what we have, okay, these are also like a kind of similar problems wherein we are asked to find the terminal velocity of the particle in SI units. So in the question, a spherical particle of diameter 0.5 mm made of steel and having density 7870 kg per meter cube falls under gravity at a terminal conditions through a liquid of density 710 kg per meter cube in a very large diameter tube. The viscosity of the liquid is 10 millinewton second per meter square. Calculate the terminal velocity of the particle in SI units. So what is asked? In the question it is asked that a spherical particle whose diameter is 0.5 mm and it is made of steel and it is having a density of 7870 kg per meter cube. It is falling under the gravity under the terminal settling conditions through a liquid whose density is 710 kg per meter cube, and it is happening in a very large diameter tube. Very large diameter tube, because then we can say that there are no wall effects hindering the movement of the particle. The particle is falling without any wall effects. The viscosity of the liquid is 10 milli Newton second by meter square, and its terminal velocity we need to calculate it. So this is a question. So what we need to do, just need to calculate the terminal settling velocity of the particle, which is very simple because we have been doing that only throughout the whole class. So we will calculate the terminal velocity of the particle. So answer is actually point, oh no, it is not 003. I changed the numericals. I changed the number. I'm having a density of, so that is the thing. We just need to calculate the terminal velocity of the particle falling through the you know liquid. So in the question also it is given that what we can do is we have two approaches. First is uh, we since we don't know the Reynolds number, we can't know in which regime it is flowing, so we can't directly use the VT formula. First thing what we can do is we can go assuming the flow regime to be Stokes regime. We can first calculate the velocity using the Stokes regime formula and later re-verify it using the Reynolds number. So first we'll do that. Given particle diameter is okay, I changed the numbers, that is the issue here. It is 0.25 mm, and so therefore I'll keep it like this: 0.25 mm or 2.5 into 10 power minus 4 meter. Particle density is steel and it is having 7870 kg per meter cube, and fluid density is rho f given by 710 kg per meter cube. Fluid viscosity is 8 millinewton second by meter square. Oh, when did I change this? Okay, question is slightly changed. Just 8 millinewton second by meter square. So it is 8 into 10 power minus 3 Pascal second. So gravity is G equal to 9.81 meter per second square. It is acceleration, right? So it is meter per second square. Now we have to find the terminal settling velocity. To find velocity, we have to find the velocity. So formula is Vs is equal to rho p minus rho f into g into dp square by 18 mu. So now we have to substitute it everything here. So rho p is 7870, minus rho f is rho f is 710 into g is 9.81 into dp square. dp is 2.5 into 10 power minus 4 meter square divided by 18 mu. Mu is 0.008. So that gives us 7870 minus, okay, what are we getting? I'll just recalculate it once. 7870 minus 710 into 9.81 into 2.5 square divided by 18 divided by 0.008 into 10 power minus 8. So we were getting velocity as 0.03049, or we can write 0.305 meter per second. So now what we have to do, we have to verify the Reynolds number claim. Verify the Reynolds number so it is assuming so RE is equal to, we can insert equation. So if you learn this now, you will get you can use it during your presentation and all. If you are BTech, it will be helpful. Others might know all these things. For BTech, we would be doing not sure of how to do things, right? That's why. And as far as I think the course targeted audience is BTech, that's why I told. So now it is rho VT. Rho is 710 into VT is 0.0305 into DP is 2.5 into 10 power minus 4 by 0.008. So that gives us 710 into 0.00305 into 2.5 into 10 power minus 4 divided by 0.008. It gives us 0.6767. And we can say Reynolds number is less than 1 following Stokes regime. So we have verified Reynolds number to be less than 1. Reynolds number successfully under the Stokes regime. First, we have assumed the flow to be in Stokes regime. Later, we calculated the terminal settling velocity, assuming the flow is under Stokes regime, and we have calculated things. And after calculating velocity, we put it back in the Reynolds number equation and checked whether it is under the Stokes regime, and we found out it to be under the Stokes regime. If value came different, you should go back to identifying it using the Newton's law formula. So that is how we get the formula, and this is how we do the solution. So I hope the solution is clear. Now coming to question 14. Calculate the Reynolds number for this fluid particle problem. We already did in the previous slide, but anyway, coming to the question. RET is equal to rho VT dP by mu, and rho is 710 into 0.0305 into 2.5 into 10 power minus 4 divided by 0.008, and that gives us 0.6767 or 6764, whatever it is. Reynolds number is, that is the value. Alright, rho f, generally rho means it is fluid, rho p means it is the particle Reynolds number. So that is how we differentiate it. Now, last before problem, what we got here is a sphere of diameter 0.05 mm and density 3.8 gram per centimeter cube is allowed to settle under the action of centrifugal force such that the acceleration is g, where g is the acceleration due to gravity. The density and viscosity of the liquid in which particle settles is 0.996 gram per centimeter cube and 0.00801 poise. Calculate the parameter k used to ascertain the regime of particle settling. So what we asked, a sphere of diameter 0.05 mm and density 3.8 gram per centimeter cube is allowed to settle under the action of centrifugal force such that the acceleration is acceleration is g, and g is the acceleration due to gravity, and the density and viscosity of the liquid in which particle settles is 0.996 gram per centimeter cube and 0.00801 poise, and we are asked to find the parameter k, which is used to ascertain the regime of particle settling. So, as far as the solution is concerned, so now first let us write given diameter of a sphere dp is 0.05 mm and its density is 3.8 gram per centimeter cube, or we can write it as 3800 kg by meter cube. Acceleration g is 9.81 meter per second square, or here it is 0.996 gram per centimeter cube, or 996 kg by meter cube, and viscosity of liquid is 0.00801 poise, which is okay, 0.00801 uh, Pascal Newton second Pascal second, and we have to find the parameter k, which is used to ascertain the regime of particle settling. We have to find the parameter k. So I'll give you the formula. Oh, okay. I'll give you the formula and now you have to give me the answer. So formula for k is equal to g into dp cube into rho p minus rho f into rho f by mu square whole to the power of 1 by 3. Okay. So now find out the answer for this, we will discuss. K is equal to g into dp cube into rho p minus rho f into rho f divided by mu square whole to the power of 1 by 3. So we can see the substitution wise. We'll do it now because since we have time, we can do the solution and check. K equal to third equation, and it is not bold, it is k equal to, so something to the power of 1 by 3 by 3. Now again we have g is 9, okay, 9 by 3, let us put. Now we have mu is, what was mu? 0.00801, 0.00801 to the power square, and in numerator we have 9.81 into dp is, what was dp? dp is 0.05 mm, so it is 0.05 into 10 power minus 3 0.5 mm into rho p minus rho f is 3800 minus 996. Oh. 3800 minus 996 into 996. So what happens now? We should calculate it. Here it is actually to the power of 3. Okay, 0.05 into 10 power, okay, it is cube, 10 power minus 3 power 3 into 9.81 into 3800 minus 996 into 996 divided by 0.00801 square. So basically it is k equal to 0.0534 to the power of 1 by 3. And now if we take to the power of 1 by 3, point 376. Actually our previous answer was different, na? It was something about 1. Actually it was 1.76. Okay, I put it as 00801, but it is 0.0801. Poise is, okay, poise to Pascal second. 1 poise is 0.1 Pascal second. Okay, 1 poise is actually 0.1 Pascal second. That is, so it becomes 0. So if that is the case, everything will change. 9.81 into 0.05 to the power of 3 into 10 power minus 9 into 996 into 3800 minus 996 divided by 0.000801 square. It is 5.3377 to the power of 1 divided by 3. It is 1.7476. Now it is right, 1.7476. So basically poise is 0.1 Pascal second. So yeah, poise is 0.1 Pascal second. I'll just check in the previous question whether if anywhere I made that mistake. Here it is given 001 Pascal second. Here also it is given in Pascal second. Here it is constant mu. Here it is formula. Newton second by meter square. Mm, mm, Here it is again same problem. Here it is poise. So 1 poise equal to 0.1 Pascal second. Confusion, which kind of gave a wrong result, but now we have corrected it and final answer is 1.7476 is your final K. K is the parameter used to ascertain the regime of particle settling. One thing would be like don't compare my numerics and check for any like physics based logical errors, because these numbers are actually given by me in the last moment, just to ensure that your question in the assignment doesn't match with this. So because of that it may have gone somewhere wrong and all. So I just request you people to not think physically logically about this. And also the parameter K is again used to identify the regime of flow. So don't do that also, like it may not match. It is used to ascertain the regime of particle settling. It may not match because again like it is not a fully physics based problem. Because of number tweaking, some physics may be going wrong. So that is my request to you people. So yeah, thank you with that request. I hope you understand, because I just want to make sure you don't have the same problem from assignment. I'm just making some different numerics. Since I don't have sufficient time, I'm just changing the numbers and physics may slightly be affected. So yeah, for that's it. Uh, for last problem for today's session, we will see now. This is going to be a last problem for today's session. In question 16, what is asked? Calculate the terminal settling velocity of the particle in SI units. Again, it is a very simple problem and a straightforward problem. And we are given that diameter of the sphere is 0.05 mm. Density of sphere is 3.8 gram per centimeter cube. And acceleration is 9.81 meter per second square. And density of liquid is 9.996 gram per centimeter cube, and mu f is 0.00801 poise. Again, I wouldn't have used proper thing. Again, we need to verify it with Reynolds number. I'll just verify this, because if it is wrong, I don't want to give you a wrong numerical. RET is equal to RET, rho VT, everything same. It is just a terminal velocity, terminal Reynolds number or particle Reynolds number. Since in the question it is asked for the terminal velocity, I am using that nomenclature. But if you use REP, it is particle Reynolds number. That won't be a change. It is, what is the thing? Rho is 996 into VT is 4.7696 into, it won't be 10 power minus 4 anymore, it would be like 10 power minus 3 into dp is 0.05 into 10 power minus 3 divided by 0.000801. What it is giving? 996 into 4.7696 into 10 power minus 3 0.05 into 10 power minus 3 divided by 0.000801. Okay, it is coming in range only. I was just afraid it might not. 0.2965. Okay, now we will go step by step of how to do, because I just wanted to make sure I went like this. So calculate the terminal settling velocity of the particle in SI units, and we are given diameter of sphere is 0.05 mm, and here also we can write it is 5 into 10 power minus 4 meter. Density of sphere is 3.8 gram per centimeters cube, or 3800 kg by meter cube, and again 9.81 meter per centimeter per second square, and here it is 996 kg by meter cube, and here it is 0.00801 or Pascal second, or 8.01 into 10 power minus 4 Pascal. I just confirm this unit once. Poise to Pascal second. 1 poise is equal to 0.1 Pascal second. Alright. So this was the thing. So now first we are assuming the flow is in Stokes regime, because we are not sure, or was it given in question? Okay, it was not given in the question, but with K we can identify the regime of particle settling, but now we haven't done that. We are just assuming the flow is in Stokes regime. We are taking the formula and we are substituting. If it is not there, we will go back to the Reynolds regime formula and check with that. So now Vt is equal to 3800 minus 996 into 9.81 into dp square. So what was 5 into 10 power 5 into 10 power minus 3, right? Yeah, it is minus 5, not 3, minus 5. So it is 5 into 10 power minus 5 whole square dp square divided by 8 into 8.01 into 10 power minus 4. So now what we can do, we can substitute it, and we will get 3800 minus 996 into 9.81 into 25 divided by 18 divided by 8.01 into 10 power minus 6 divided by minus 4. So minus 10 divided by minus 4, it will be minus 6. So it is 4.7696 into 10 power minus 3. Yeah, it is minus 3. Minus 3 meter per second. Because we changed, right, that I haven't included here, that is the confusion. Now RET, we are verifying Reynolds number. Reynolds number to ensure flow is in Stokes regime. So rho we can put it as rho F also. Rho F Vt dp by mu is the Reynolds number formula, and rho F is 996 into Vt is 4.7696 into 10 power minus 3 into 5 into 10 power minus 5 divided by 8.01 into 10 power 4. So it is 0.2965, that is right. So we will change here and all. 5 into 10 power minus 5. 8.01 into 10 power minus 4. So it is 0.2965 So what happens? RET is less than 1. Flow is in Stokes regime. So verified. We have verified. So this VT is correct only. What was asked? We are asked to find it in the SI units only. So we can say that VT is equal to this, and we can say it is in meter per second. 4.7696 into 10 power minus 3 meter per second. So that's it for today's session. Yeah, here also we can write 5 into 10 power minus 5 into 8 into 10 power minus 4 Pascal second. Minus 4 Pascal second, 8.01. Everything else I guess is right only. 5 into 10 power minus 4. Let it remain, not an issue. Alright, that's it for today's session. In today's session, what we have seen, we'll just have a quick recap. We have mostly seen about terminal settling velocity, terminal velocity only, with different approaches. First one is a match, and we have seen Stokes regime, Newton's regime, Stokes-Einstein relation, Einstein theory of diffusivity, Brownian force. So we have seen explanation for each, and we have seen about drag force is a function of particle projected area and particle drag coefficient. It should be both A and B. Again, particle Reynolds number. So particle Reynolds number is rho v dp by mu. If we know that, we can answer 2-3 questions. And later we are asked to find the settling velocity by framing the question in a different way. And also make sure in what units your question you are asked to report your answer, because since it is a numerical problem, make sure you report your answer in the unit they asked. In some question it is a SI unit, some question it is in micrometer, per second, or something. So whenever you are finding out the answer, just make sure you give your answer in the desired units which is asked in the question, because it is not a multiple choice questions for all the problems. Some are where you need to give your own answer. So in those cases, you have to make sure your answer is in the proper unit. Otherwise, you might uh, lose marks. So just identify the question and give the proper response. Read the question more than once. Again, it is asked to find the largest diameter of the particle, which is obeying Stokes law. So we combined Reynolds number and the Stokes law equation and found the answer. And later it is about identifying the force formulae. And at last we had few problems of identifying the terminal velocity, and we compared it with the Reynolds number. If the Reynolds number is going out of range, you need to check for the Newton's law regime, and by using that VT formula, and later again verify the Newton's law regime Reynolds number or not. That is, first use the Newton's law terminal velocity formula, and from there check whether your terminal velocity is obeying the Reynolds number in the Newton's regime or not. So these are the questions which we saw in today's class. So yeah, thank you for today's session. We will meet again next week on the same time, 3 p.m. to 5 p.m. on Saturday, with few more interesting problems related to week 7. So yeah, that's it for today's class. If you have any doubts, we can discuss, or else we can close the session. I'll stop the recording as well. Thank you.